All right, so last time I looked at the translational stability of an object. That was what is the state of forces that keeps an object in place. And that basically said that all the forces have to be balanced. Everything has to be opposed by something else. So if there's a wind pushing something, then there should be some drag, or there should be some sort of other force, frictional force, let's say, that keeps the thing from being pushed by the wind, right? So you could imagine if you put a box on some ice or something on an icy lake, the wind could push it across the lake. But that wouldn't happen if you put it in the snow or on the concrete or something like that on the blacktop. Now we want to look at rotational stability, and this is something that would keep something from twisting away. So why does a diving board stay where it is, right? I mean, the center of mass of the diving board is above the water, so it should rotate. But because there's something else called a torque that's keeping it from rotating, it doesn't rotate. So we'll talk a little bit about that here and really just get a feel for that. That's going to be sort of the last thing we do in the class, are torques, I think. But historically, the law of the lever comes around with Archimedes and stuff like that. So it's one of these really early things that we learn about. The balance of torque, although it wasn't called torque at that time, was one of the first things that we knew that was really, really important in physics, that was a real principle of physics that we're going to keep later on. Now, rotational stability basically says that if an object is not going to start spinning, right? If an object A is not spinning, let me call it rotating. Could be rotating around any axis, and does not start rotating, then the torques on the object cancel. Okay, so that just means that if we have a bunch of things pushing on a object, right? If let's say you had a merry-go-round, a playground merry-go-round, right? And you were trying to push it this way. You were about 6 apparently, and your friend was on the other side trying to push it. You're both pushing in the same direction, but you're trying to rotate it. Let's see, that looks clockwise, and your friend is trying to rotate it counterclockwise. The merry-go-round just stays in place. So you have to be rotating in the same sense, or pushing in the same sense, to make the merry-go-round go faster, because your sister's here and she wants to have a good time. But you're working against each other, so nobody's having any fun at all. So that's basically what we're saying, is that the torques, and we call that N for some reason in this class, mostly because we don't get into Greek letters. Normally it's a tau, which is a Greek T, but it's not really that important. Occasionally I've run into that. So if you have a whole bunch of these torques and they add up, some going clockwise, some going counterclockwise, if they end up at 0 and the thing's not rotating, it does not start rotating. That's rotational stability. So we have to have some idea about what's going on, right? So we were looking at this where we had you pushing this way and your friend pushing this way, and it was basically equal. So in some sense, these are equal. They're going in the opposite directions. One's negative and one's positive. But there are some other things. It's not just the push that's important, right? But the torque is caused by pushing around an object, right? So this is the object. This is the spot where it spins around. So the torque is going to push, or it's going to try to make it spin, again, counterclockwise, right? And here, this is where you're applying the force. It's trying to do it this way. So the torque is caused by pushing around an axis, an object's pivot point is one way we can talk about it. Use all sorts of words for this: pivot point, fulcrum. Sort of depends on axle. An axle is another one. Axis is an axle. These are all of these things. I think this would be an axle. All of these things basically mean the same thing: where the object's going to spin around if you try to make it spin. All right. And it's only the force that's actually perpendicular to the distance to the axle. So if I was pushing sort of, let's see, this way, only the stuff going this way would happen. So, you know, if you're pushing with your foot, you might be pushing along this way because your foot's out this way, right? So you've all pushed the merry-go-round on your foot. So you, with your foot at some point in your lives, and you know, it's going to try to go in that clockwise direction, but it won't be efficient unless you're pushing straight back perpendicular to, I guess technically tangential to your merry-go-round. So only the perpendicular, what we call component of the force, causes the torque. It's too much red already. I'll change my color. Okay. So let's look at another sort of example. We've got, let's say, a nut, a wrench, right, like that. And you know, your hand is going, you're going to have your hand out here somewhere, right? So this is the point of application, right? And you know that if you were to pull this way or to push this way, right, straight along the handle direction, you're not going to rotate that nut, right? So this is the component of the force parallel to this thing, this wrench, or yeah, the wrench's handle, which is where you're going to do it. If you push directly towards the handle, you're going to get the maximum effect, right? If you're pushing straight down, you get the maximum effect. In fact, this is all the effect you're going to get. If you were to push over this way, you get a lesser force, right? So this is your push. This is your push that's perpendicular to this handle. And this is small. This is the component of, this perpendicular part is the component of your full push, which is obviously smaller, right? This is like the diagonal of a triangle, so it's larger. You can use trigonometry to find these things, and we probably will towards the end of the class. But so we're pushing, and this is the only part that's actually giving us the force. So that's one part of what we're doing. The other part of the torque is this distance. right? The farther out you go, the farther out you can go with your hand, the more torque you get, right? So you're pushing this way, out this way, you get more torque, all right? So that's extremely important, right? So that's how we get our definition of the torque, right? The definition of the torque is N, the torque. I've got too much stuff already, and I broke it up into stuff. All right, is equal to the distance from the center of the thing that you want to turn, or from the place you want to turn it, from this pivot point, to, and the nut is the pivot point, the place where you're applying the force, the place where your hand is pushing on that wrench, times the perpendicular part of the push or the pull of the force. Perpendicular component of the force. I'm at the edge. Need to remember to put lines there. Okay, so that's more or less what the torque is defined as, right? So we push down, the nut turns clockwise. Makes sense, right? And the farther out you go, the more torque you will get, the more torque you can apply to that nut. You don't always want to apply more torque to that nut, right? You don't want to break your screw. Over torquing is bad. I just had an over torquing incident, so I'm trying not to talk about it. And so farther out, more force. That's what you get, more torque. This is the reason for one of the most important things. This is actually Archimedes' contribution. The law of the lever. Right? And a lever, basically you have a fulcrum, you have some distance here, some distance from the fulcrum to where you apply your force, and then you have, let's say, a box here, so you have a smaller distance d here, and then that's where the weight is applied. Right? This is basically the law of the lever is going to tell us the minimum distance that we need to lift this box. Okay, based on all of these things, and a problem will probably say how long the lever is, and something like that, and how much the weight is, and how much you have to ask you how much you have to apply for this, or maybe it tells you how much you can apply for this and tell you to figure out what that D must be, or something like that. So there'll be a little bit of thinking involved, but that's where the world is. There's got to be a little bit of thinking. So the law of the lever really just tells us what we were talking about right here. We were saying that if you come out more, you get more force. If you come in, or more torque, and if you come in, you get less torque. And we want to balance out those torques. And the last place that those things balance out, or the place where just you and the box are balancing it out, because if you have less force, if you're pushing with less force, then you need to pull this up. The ground is also keeping this weight up, so the ground is pushing up on the box as well. So it's only when you just start pushing with the exact amount of force to balance this out that you get the law of the lever. That's the amount of force you need. You want to have more force than that. The more force you can apply, the easier it is, right? And that's why you lift weights, right? Is so that you can do things like this a little bit easier. And so we're trying to apply this and this at the same time. The law of the lever, watching too many British sitcoms or something, says that if you have a big force here, or here, and a small distance, d, it's equal to a small force and a big distance, right? Let's make these bigger, right? Big force, small distance equals small force, big distance. That's the law of the lever, right? So a large block at a close distance equals, or a large force at a close distance equals a small force at a large distance. Right, and remember, this is the minimum force F to lift a weight, a big weight, F, big F, right? So you want your work to be as little as possible to lift as much as possible. And that's why the lever, as a simple machine, is one of the most important things that people figured out in 400 BC or whatever it was. So that is more or less what I've got for rotational stability. I'll do one example, and after I do that example, I'll go on to the more general idea about inertia. All right. So I hope that's sufficiently clear. I'll see you again in a few minutes. Bye now.